So let's start our morning session. Our first speaker is Umut Varolgunes, who is going to tell us about homological mirror symmetry via Floer theory with support.
Thank you. So even though the title says Floer theory with support, I kind of wanted to give a lecture that doesn't get into the Floer theory with support and kind of talks about more well-known structures in the first lecture and try to kind of present the strategy for homological mirror symmetry in a case where you can just kind of work with invariants that were defined before this kind of Floer theory with support. Okay, so that's like symplectic cohomology for Liouville domains or wrapped category. And in the next lecture, I'll define Floer theory with. Okay. So just some basic definitions first. So by Liouville manifold, I mean a complete finite type Liouville manifold. So that's okay, that used to work. Can you see this?
Yeah.
Okay, so this is the Liouville one form. So its exterior derivative is the symplectic form. And you can define a Liouville vector field. Let me just show you the Liouville vector field. So omega is the symplectic form. So this is the exterior derivative of this lambda. And the Liouville vector field is the omega dual of lambda. And that's a kind of exponentiating vector field. It doesn't preserve the symplectic form, it exponentiates it. And examples that are relevant to us today, most important ones probably, are these smooth complex affine varieties. And you get a Liouville one form if you kind of embed them into Cn, just choose any presentation of the affine, the ring of functions, algebra of functions, and take this kind of standard PDQ form from Cn and restrict it. Okay.
Yeah, want to take the symmetric one, PDQ minus Q.
I can, yeah, let's take the symmetric one, maybe, yes. That's right, thank you, yeah, that's better. Yeah, sorry,
the radial.
Thank you. So it's better to take PDQ minus Q dp. I wrote this in the brush. So it's the standard radial Liouville vector field. So you have the standard symplectic form on Cn, and you take the radial vector field as your Liouville vector. Okay, so yeah, thank you. Okay, so that's my basic kind of ambient manifold, and I will try to restrict until kind of the very end to Liouville subdomains. And the Liouville subdomain is a compact domain inside my Liouville manifold, such that the Liouville vector field points strictly outwards. Okay. And I choose, so I work in the graded setup. So I assume that the first Chern class is trivial, a 0, and I fix grading data. So if you know what this is, great. If you don't, I can equip my invariants with Z gradings with this data. Okay, Philip, please keep your policing. Yeah. Okay, so now I'm also going to consider Lagrangian submanifolds inside my Liouville manifold. So they will be proper, not necessarily compact Lagrangian submanifolds. And I will call them exact. This is actually hard for me to see myself. Okay, so exact, maybe I should try to do it from here. Okay, so I will call it exact if the restriction of the Liouville one form is exact on the Lagrangian. Okay.
Proper, you mean?
No, proper, I mean properly embedded. Which means that if you intersect it with a compact set, then it's compact. Okay. Then I will call this Lagrangian conical if the Liouville vector field is tangent to it, and I will call it conical at infinity if it's tangent to it outside a compact set. Okay. Okay. So now the invariants that I can consider in this setup are called symplectic cohomology, wrapped Fukaya. Of course, there are others, but these are the ones I'll talk about. So symplectic cohomology is a BB algebra. And so I'm saying that I'm working over a commutative ring K, but the reason why I'm not like I could work over the integers for most of the story, but sometimes I have to work over a field. I don't want to spend time with this. Okay, if you're particularly worried about how I'm choosing my coefficient ring, please email me. We can resolve this issue. Okay, I don't want to talk about it. Okay, so I say it's a BD algebra, but really the part of it that's going to be most relevant is the degree 0 part of this. That's just a commutative algebra. Okay, the degree 0 symplectic cohomology, commutative algebra. I mean, the construction is relatively involved, and I will give a construction of a more general invariant that specializes to this in the next lecture. Today, I'm just assuming you've heard of this. Okay, and if I have a Liouville subdomain, this M in is a Liouville subdomain, and this hat thing is, it means that I take that Liouville subdomain and I attach a semi-infinite cone and make that complete. Okay, so that's also this M in hat is completed Liouville subdomain. And I obtained, so part of the structure is that you have restriction maps. So if you have symplectic cohomology of M, you can get maps to the symplectic cohomology of the Liouville subdomain. So it respects the BV algebra structure. And moreover, if you deform M in through kind of Liouville subdomains, then the map doesn't change. So, I mean, again, it's some sentence that you have to think a little bit about. Though. It's not like, yeah, this invariant is not sensitive to size. It's relatively qualitative invariant. Okay, and we can also talk about wrapped Fukaya category. So this is an A infinity category. And its objects are exact proper Lagrangians, which are conical at infinity with some grading and spin structures. And okay, there's the cryptic comment that I'm allowing empty subset because, yeah, it will just come up in Viterbo restriction maps. Okay, so now what I want to do is to do the same kind of thing, is to define the same kind of restriction map or restriction functor, which should be an A infinity functor now. But unfortunately, there is kind of a caveat here. You can't define this restriction map in the way that I will talk about for all the Lagrangians that are the objects of this category. You have to make a restriction on the objects. Okay, so this point, I mean, it's very carefully explained in the original paper, Abouzaid Zaidel. And somehow, like, because of this condition, these maps are often dubbed in the literature as strange maps, even though they're not strange, they just need some, constraint. You want to define it, but I think they're pretty interesting maps. And then if you want, like, there's a paper of Zach Silvan who tells you that you can extend it to all Lagrangians, but you have to do something more. You have to go to, instead of mapping to the, okay, let me just go to this. Instead of going to the wrap category of the smaller domain, you have to go to perfect complexes over that, and then you can define a map. But I'm not going to do that. So now let's, which Lagrangians I'm allowing. These are the ones that can be equipped with a primitive that vanishes in a neighborhood of the small domain, and also at infinity. Okay? It's a non-trivial condition. There are examples, again, you can look at Abouzaid Zaidel, some kind of examples in T star S1 where you don't expect to be able to define Viterbo restriction maps without this assumption. It's not some exotic phenomenon. It happens.
Yeah, so this you say e.g. conical ones. So how?
Yeah, if it's conical, then just data vanishes on. So then you can choose this primitive to be just 0. So conical ones are, yeah, thank you for asking. If, like, I'm allowing this kind of stranger class of Lagrangians because it gives me some flexibility for perturbing Lagrangians.
No. So the M in is a thing that the rest is conical.
No, M in is no, it doesn't have to be.
I see anything.
It's any Liouville subdomain. It's not a full Liouville subdomain.
Then you add this. For the hat, you add the.
Yeah, hat means add. Yes. Yes. So now, I mean, it would be kind of nicer if I just could work with conical ones because it's a condition that's invariant of the domain. Like it doesn't depend on which domain you pick. But it helps me to relax it a little bit because then you can do some Hamiltonian perturbations and you can still allow. Okay. But I will still call that subcategory every time I hopefully point. I will consider that subcategory W conical, even though it's kind of an abuse of notation because this this kind of condition actually depends on n in. Okay. You look very confused, but this was something that was there from the beginning. It's in it's in the original paper. Okay, so now, so kind of one of the lessons of homological mirror symmetry is that we shouldn't kind of try to, well, if you want to kind of just compute invariants, it's too hard to compute these A infinity categories, but we should try to compute their kind of triangulated split closures. That's more accessible. And so I say that a subcategory split generates, a full subcategory split generates. I will usually consider just full subcategories. If the induced map on the, so this twisted means I'm taking triangulated closure and pi means I'm taking split closure. And when I go to the homotopy category, this should be an equivalence of triangulated categories. Okay, so that's what it means for A to split generates. Okay, this means that if you embed, maybe let me go to that. So I'll give you an alternative characterization. So alternatively, you can say this as, you can define a functor from the wrap category of M to modules over the subcategory, okay, by restricting the Yoneda functor, which means that I only test with the objects that are in A and define an A infinity functor that way. You can also think of it as you take the usual Yoneda functor and then compose it with the canonical map to the subcategories module. Okay, so saying that the subcategory split generates is equivalent to saying that this restricted Yoneda functor is cohomologically fully favorable with image landing in perfect complexes. The perfect complexes in mod A are those exactly that can be built from the image of A and taking cones and summits. So this alternative is actually a more convenient way of saying this. Okay, and there's a big theorem in the field, which is this generation theorem. Okay, so these people, this is Chantrain, Dimitrov, Rizal, Golovko, Gigini. That's one group who proved this result, and also Ganatra-Sanda. This one's much more famous, but I don't know. I think this one's equally good. I'm not sure why. Okay, but so now if we make an extra assumption on M, we assume that it's Weinstein. Okay, I'm not going to introduce this, but it's a condition that holds, for example, for affine varieties. The Liouville manifolds that come from affine varieties are Weinstein. In that case, there exists a finite collection of conical Lagrangians that generate. I didn't tell you what generate means. Generate means you just remove this pi. It's a stronger condition. So they prove the stronger thing, but I will only use split generate today. So this finite collection, these are the co-cores of a Handel decomposition. They generate the wrapped Fukaya category. Okay, it's a big theorem. Okay, so now mirror symmetry. So I will kind of keep it simple and say that if I have a variety over Y whose derived category of coherent sheaves is isomorphic to this kind of homotopy category of the triangulated split closure of the wrap category, I will say that this variety is a mirror. Okay. If its category of coherent sheaves captures the wrap category, I will say that it's a mirror. So there are two important cases here. One is what usually is called large volume limit. So here what you do is you take a complex projective smooth Calabi-Yau variety and you remove an ample divisor from it. And you look at so you take an ample divisor and you remove it, and M is this complement. And here the grading structure is the one that extends to the compact guy. Okay, so this is the large volume limit. So you just kind of remove the ample divisor. This is kind of Seidel really popularized this. Sheridan used it a lot. This interpretation of what large volume limit should mean. So this, so I'm not gonna focus on this case. So I'm gonna quickly just review the literature. So this is actually established in many cases. So probably the most famous one is this very affine hypersurfaces by Ganatra-Sanda. So that belongs to this case. That's recently been generalized to very affine complete intersections, maybe a little bit more assumptions by this, I think he's a student of Sheridan. And there was also this kind of framework of manifolds that Ganatra and Sanda defined, which is not exactly a new thing, but I think it encapsulates the geometry that comes in to this type of mirror symmetry pretty well. It's very related to fan structures. Yeah. Okay. So now, in this case, often the mirror variety is proper, it's compact. And also, there is this, so this guy is non-proper, so the mirror should either be non-compact or singular. You can't have a smooth, proper mirror in this case. So in the large volume limit, it is kind of, in applications, it's often proper, but it's singular. And you can also prove usually that if you look at the subcategory of the wrap category, which consists of compact exact Lagrangians, then that corresponds to considering perfect complexes on the singular array. Okay, but the case that I'm gonna return to this large volume limit case at the very end, if there's time, with an example. But the one that I want to focus more on today is this local, I like to call local symmetry. In this case, you start with a Fano and remove the anti-canonical divisor, remove an anti-canonical divisor. In this case, the grading structure does not extend. It has poles along the boundary divisor. Okay, so a different case. And I will call this local mirror symmetry if the mirror itself is also a smooth affine variety. So now let me give you some examples. So there is this kind of general conjecture that involves kind of a switching. Okay, so there is this general kind of Batirev-Borisov construction that I don't want to detail here, but there is a kind of a natural class of local models that you can cover Batirev-Borisov spaces with. And these local models are indexed by some pairs of minimal integral simplices. I don't want to try. So if you have questions, you can ask to Ilya.
No, the question was the minimum.
Minimal just means that you can't, like, it doesn't have any integral points other than the vertices.
What they call elementary.
Yeah. Okay. Minimal sounds okay, right? Like you can't find another smaller one inside. Okay. Anyway, so these two play two different roles, and mirror symmetry is supposed to exchange them. Okay, but I want to talk about the case that's easier to talk about, where these minimal integral simplices are unimodular. So that corresponds to this spaces. These guys, where here xi's are complex numbers and yi's are elements of C star, or K versions of that. Okay, so x's can vanish, y's cannot vanish. So you define this explicit YKL variety, and mirror symmetry is supposed to exchange this K and L. Okay, and mirror again in the sense that I defined this, like DB co is equivalent to that category and so on. So I always mean that. And this is now a proved statement. There's one proof by Abouzaid and one proof by Gammon. With this one, you have to be much more careful because you have to now deal with orbifolds stuff. So yeah. But if you want to prove general Batira-Borisov mirror symmetry using something like S by Z, you're going to have to deal with these more generally. Okay, so that's just so this covers a lot of the kind of, usually people start with kind of cotangent bundle of a torus. The cotangent bundle of a torus corresponds to taking K or L to be 0. And you can check the other side is also, so you think of it as C star to the n, the other side also becomes C star to the n, so that's self-dual, that's part of this. Another one that people talk about a lot is the C2 minus a conic. That's also self-dual, that follows from this as well. But there is, I think, a principle behind kind of being able to say something like that. And I don't know, I attribute this principle to Dan, but maybe he can correct me if it's someone else. So in this principle, so when does local mirror symmetry, when do I expect it to hold? Well, you start with an affine log Calabi-Yau interior. Okay, so some log Calabi-Yau whose boundary supports an ample divisor. So the complement is affine. Okay, so it gives me a Liouville manifold, and it should admit a toric model. Well, so Dan's condition is weaker, but I don't know how to get that condition without assuming a toric model. The toric model basically means you start with just a toric variety, and you do blow-ups along the boundary, and you remove the proper transform of the boundary divisor. Okay, so that always gives you a log Calabi-Yau. And not all affine log Calabi-Yau interiors have such a toric model, but it's a big class anyways. And these satisfy that condition. And if you have a toric model, this kind of, you can construct a nice Lagrangian section. There is no fibration, but you can construct a nice Lagrangian, and you can say, well, you can give a precise definition of what it means to be a homological section, and check that it holds under some kind of geometric conditions. That's in Dan's paper. Okay, so that's one part. And the second assumption is that this symplectic cohomology, this commutative algebra, its spectrum should give you a smooth variety. Okay, so that shouldn't have any singularity. So if these two conditions are true, then I claim that this is the principle for this local mirror symmetry for M. It will hold. So then kind of, if these conditions hold, then you can consider this this Lagrangian, do its Lagrangian wrapped Lagrangian Floer homology, and that's actually isomorphic. So it's supported in degree 0 and isomorphic to degree 0 symplectic cohomology, commutative, for example. Yes.
Is YK, they're all log Calabi-Yau, right?
Yeah. Interiors. Yes. So then instead of considering SH0, you can just consider the Lagrangian Floer homology of the section, this homological section. And this Lagrangian section split generates the wrapped category. It's kind of also a good result. It uses GPS. Now I found just one Lagrangian that generates the whole thing. Okay. And therefore, I can say that this spectrum of the degree 0 symplectic cohomology is a mirror of M. And moreover, it's not just some arbitrary HMS functor. There is a manifest HMS functor given by restricted Goneda functor. Okay, so that's an equivalent. Okay, so that's good. So now you want to kind of understand when does this hold, SH0M being a smooth algebra. So it turns out the reason why this is not like the most famous theorem in the world is that it actually is not that common. Okay, so I mean, but it does hold in these, it explains these kind of very fundamental examples. But I don't know if there are many more examples where you can use this. But of course, Dan's paper has more. So he then kind of considers a weaker assumption. So M is here. So if M is the kind of complement of the divisor inside this XD log Calabi-Yau, where again it's positive, there's an ample, so it's affine, M is affine. So this is dimension n, and there is this kind of assumption that he makes, which is the strata of the divisor are all connected. And you can ask him about it if you're curious about this assumption, but it's maximally degenerate. Okay, so it has a point where n divisors intersect. Okay, so under this assumption, which is really not that strong, he proves that this spectrum of SH0 is a reduced Gorenstein n-dimensional scheme of finite type, and it's Calabi-Yau. Okay, so it's not smooth necessarily, but it's like something that approximates what you expect as the mirror pretty well. Okay, and then he continues by saying that he proves that the wrapped category is what Kuznetsov defines as categorical Krepin resolution of this singular affine variety. It's like a precise definition, and he proves that this is true in this case, so it's not just some philosophy. The part that's philosophy is that Kuznetsov apparently also claims that there is some kind of uniqueness for categorical Krepin resolution. So that would imply that if you have any Krepin resolution of the singular affine variety, that would be a mirror. So now, what is my goal? My goal is that I claim that you can do something a little bit finer, some more local construction, so that you can actually construct these some Krepin resolutions by gluing spectrum of degree 0 symplectic cohomologies of some Poisson commuting cover by Liouville subdomain. I want to construct these Krepin resolutions from the geometry, not just assume that they exist. And, okay, so now let's go to an example. So any questions up to now? How am I doing on time?
Half an hour, a little more, 35 minutes.
Okay, so here's my example. So I take CP2, and then I want to blow up the boundary. So there are three lines at the boundary, toric lines. I want to blow each of them once and remove, so I blow them up, and then I remove the boundary. So I get some local Calabi-Yau. This is a toric model. Okay, and so if the 3 points that I'm blowing up on CP2, if they're not on a P1, if they're not on a line, then the result of kind of this removing the proper transform of the boundary is an affine variety. You can write an equation. Of course, there's some moduli, but this is one affine variety that you can obtain in this way.
Can I ask a simple question? So instead of blowing up these 3 points and removing the proper transform, why just not remove the boundary stuff? It's the same.
Because that's not that's just C star squared.
In the end, you removed all the stuff which you created together with the starting boundary.
I didn't understand.
Say you remove the proper transform the boundary.
Don't remove the
other stuff
you blew up.
The exceptional curves, you just remove a point from the exceptional curves. You don't remove, because if you remove the exceptional curve, then you will get back
that's what
that calls something else.
Yeah,
what I mean is that you just remove a point from each exception. So you added like three planes, three complex planes. Okay. So this is an affine variety. So it's a symplectic manifold. It's a Liouville manifold. And I can actually represent this by like very explicitly. Maybe I just do that first. Okay, so there's a symplectic picture for this this triangle on the left. So don't ignore these shaded triangles first. So that's the moment polytope of CP2. So symplectically doing these blowups correspond to removing these triangles and adding a nodal point, a focus-focus singularity above each of these crosses. So really what I do first is I just kind of remove triangles with tips along this kind of central, affine central point, 1, 1. And then I do some movement of worms to separate out the points. So now I have kind of this, I remove these triangles. There is some monodromy created here. Now I glue this end to this end. such that the edge glues to the edge and the edge glues to this one, so that determines what the monodromy should be. Okay, so this is now an integral affine manifold with singularities along these crosses. And if you remove the boundary, of this triangle, and if you complete it, okay, you get a picture that looks like this on the right. Okay, so it's the whole plane that I make this kind of introduce these monodromy invariant lines, these branch cuts in this way. Okay, again, I hope you've seen some picture like this before. If you didn't, it's a little hard to understand. But what I'm doing is I'm just coming up with a explicit Lagrangian torus fibration on that affine variety. Okay? Yeah, so back. So now I have this kind of the rays of this Lagrangian torus fibration, the eigenrays of this Lagrangian torus fibration just kind of are along the fan of P2, the rays of the fan of P2. The mirror of this variety is computed, it's known. I think it's first computed by Keating, but maybe someone else computed before, I'm not sure. Then there is a generalization by Keating and Hacking, and Gamage and Le also proved a version of it. So it's actually very simple. The mirror is obtained by doing the following thing. So you take those rays, those define a fan, take the toric variety of that fan, and then each cross on the eigenray gives you a prescription to do, like how many times do you have to blow up along that corresponding toric divisor. And you do, so in this case, you're just supposed to take the P2, blow up each boundary divisor once, so just exactly like how we started. But now, these 3 points are supposed to be on a line. Okay, so now this variety, this mirror that I'm constructing contains a P1 inside, a -2 curve inside. Okay, and that -2 curve, the -2 curve is mirror to a Lagrangian sphere that you can actually see in the base. There's a Lagrangian sphere. That's a tropical Lagrangian sphere that you can see, and it has a mirror that's this -2 curve that's obtained by proper kind of taking the transform of this line that contained my original blow-up points. Once I blow up, it just separates from the boundary and it starts living in the interior. Okay. So now, to this affine variety, let's try this kind of Homological principle. You can compute the SH0. I mean, it's not completely trivial. You have to do some work, but you find that it's equal to this, generated by x, y, z, and the relation is x, y, z equals x plus y plus z plus 2. Okay?
Can you say who is X, Y, Z?
Who is x, y, z?
Yeah.
So it's like it's the generators that correspond to the faces. You can give a presentation of SH0 by one generator that corresponds to every boundary edge. And then there is some, it's like this intrinsic mirror. Yes? Okay, but you can also do a symplectic computation using techniques in Liouville and Groman. It just kind of repeats the kind of structure that Band and Mark uses in their computations. Okay, but what's the point? The point is that this is singular. Okay, this thing, if you compute it, has an A1 singularity at the point -1, -1, -1. Okay. And now, and if you check this Keating mirror that I talked about, like in the 2 bullet points before, that's really a crepant resolution of this singular affine variety. So that singular A1 singularity became a -2 curve. Okay. Okay, so now I want to give another construction of this correct mirror by gluing. Okay. So what I do is, So I didn't say I should add one more thing. So this is my symplectic manifold now. And you can also construct a Liouville structure and obtain like a Liouville vector field in the total space in the symplectic manifold, which is related by the projection to the base, to the vector field in the base, that is the Euler vector field, the radial vector field. You have to do something near this intersection, near this nodal points, but you can just fill those. Okay? But in the rest of some small neighborhoods of the crosses, it just really looks like the radial vector field, which that because of this kind of, because these rays are along kind of, they all pass through this point, it does kind of descend to the integral affine manifold that you obtain by introducing these branch cuts. Okay, so therefore I can cover the base. Well, I can take these subsets of the base, which are Liouville subdomains. This one, and this one. Okay. So those are Liouville subdomains. And these intersections, any double intersection and also triple intersection, those are also Liouville subdomains. There are corners, but it's okay. Corners. Okay. So Pi means, so P1, P2, P3, P1, P2, P1, P3, P2, P3, and P1, 2, 3. I take all of them. Okay. So all subsets of 1, 2, 3 can be used as this capital I index. So that's the kind of subset in the base. If you take the preimage and complete it, then you get a complete Liouville manifold that I call M sub I. Okay. So now the goal is to consider the SH zeros of all of these MIs, so M1, M2, M3, glue them along kind of the restriction maps to the kind of intersections and get some space. And I want to note that there is also a Lagrangian section in this picture, okay? And that satisfies kind of this dense kind of property. It's really a section. So instead of doing SH0, you can also do Lagrangian wrapped Floer algebra of that Lagrangian. Okay. Oh, so did I introduce? Also, this AI is the SH0 algebra for each of these subsets. And now I get this diagram. So these are A1, A2, A3. They have restriction maps to the double intersections, and then there's a triple intersection. So the maps from double intersections to triple intersections are all isomorphism. They're just domains whose completions are just the same. I need to tell you what these restriction maps from AIs to double intersections is. And I claim that those maps are localization maps. Okay, they invert some generator. So you can compute the AIs, and the AIs exactly look like this. Okay, X, Y, and then invertible U generators, and XY equals U plus 1. Okay, so, and I also know that these A12s, when you complete them, you just get T star T2. So those are Laurent power series. So I just need to tell you what this map is. And I claim that this map is just inverting one of these X or Y variables. Okay, so how do I prove this? So let me redraw these Liouville subdomains as like rectangular objects like this. So this dot is where I had like where there's the exact Lagrangian torus, and this is the same. So now I have a generator coming from this edge, this edge, this edge, and this edge. Names X, Y, U, U inverse. And when you take a rectangular subset, I mean, if you want to draw a really correct picture in a chart, you have to draw this edge band. Yeah, but I didn't do that. So now you can check that in this matching edge, X must map to X, because there is a constant solution here, and there can't be any other solution because action of any solution should be 0. The action of those generators are the same. So there can't be any other solution, so that's just that solution. X must map to X. The same with U and U inverse. What we don't know is that where does this Y map? But because this map is an algebra map, y must map to the inverse. Y must map to wherever it must map to. Okay. It's determined from this. And the point is that x times y, so x used to be not invertible. But when you go to the smaller domain, x is not invertible. So this actually is a map that localizes at x. Okay. So now I know what these maps are too. These maps are as well. And you can check that if you do this gluing of spec AI, so each of these spec AIs are this C2 minus a conic. And if I glue them along images of the intersections, like the restriction map gives you a subset that's an open subset, Zariski open subset, and I can glue these three things along those Zariski open subsets because they all are identified with the same A1, 2, 3 algebra. And the result is exactly this Keating's mirror. Each of these spec AIs are like a C star square plus a plane. And Keating's mirror is like 3 planes. It has extra 3 planes to C star square. Okay, great. So now I have given you a construction of Keating's mirror by local to global gluing. So now I want to, this is probably kind of the part of my talk that I would like you to kind of remember the most. So there is this kind of fundamental diagram. So this is a construction of the manifest HMS functor that I keep talking about. So in Dan's case, if you didn't have to glue anything, you just have this restricted Yoneda functor. So in this gluing case, you need to do a little bit more. So first you have kind of this M's wrapped Fukaya category, and you have this kind of wrapped Fukaya categories of these pieces, and you take some check construction. Okay. So it's it has well, I think you know what check construction is, and you have to check that this actually can be extended to give you an A infinity category. So morphisms use the check construction. And the point is that like I could actually skip the check construction and just go to the homotopy limit of these categories. You know what this homotopy limit of A infinity categories is? This check complex is just a part where kind of the map, so homotopy limit means you're in a diagram of A infinity categories, you choose an object, and then you map it to by a map, and there is an object that you had previously chosen there as well, and then you fix a map between them. And you keep doing this so it's some Grothendieck deconstruction, and then you do something to the Grothendieck deconstruction. Here, those maps that you choose are the identity maps. The check construction corresponds to doing that. Okay, but there is a canonical map from this, like this conical, kind of weakly conical Lagrangians in M to this homotopy limit of the local A infinity categories. Okay? And this one is a cohomologically fully faithful map. Okay, that's a non-trivial theorem. So this map to the check complex is cohomologic. That's actually an equivalence, quasi-isomorphism, and that's kind of that follows from my thesis work. Okay, I mean you have to do more work on top of it, but the idea is that. 1 second, and this map is just by abstract nonsense, it's cohomologically fully faithful. Okay, so now I can go from here to here, and now I use the fact that this Lagrangian that I chose, this Lagrangian section, actually split generates each of those pieces. It's another thing that you have to prove. It's not obvious, but it's true. For example, it follows from Dan's theorem. These are smooth algebras. And therefore, you can obtain a map from this diagram of A infinity categories to this diagram of A infinity categories, which are just perfect complexes over the endomorphism algebra of that Lagrangian section. And this map exists because of local split generation. So there are these restriction maps here, and there's the restricted Yoneda functors, and there's the kind of the push forward functor. That diagram doesn't always commute. You have to have generation. You have to be able to build build the objects here from the objects here, so that like just going here, you can recover the tensor product here at some condition. Okay, the restricted Yoneda functor diagram doesn't always commute. It commutes if you also have split generation. Okay, so you have this. And because the diagram maps to the diagram, you can go to homotopy limits, and it's also a cohomologically fully faithful map, a functor. And then this homotopy limit of perfect complexes over these, this Zariski cover, is essentially by definition a DG enhancement of the category of perfect complexes over the scheme that we glued. Okay. So I obtain a cohomologically fully faithful functor from this kind of a wrapped category, like a full subcategory of the wrapped category, but it generates, we know, by the generation results. So I can get a map from the full wrapped category to here as well. Okay, so this is kind of the basic yoga of what I'm doing. Okay, any question? Yes.
So you mentioned your thesis, so I guess what you need for these MIs are to be Poisson commute.
Yeah, they Poisson commute because there's a Lagrangian torus fibration. There are pre-images of subsets of Lagrangian torus fibration. The base of Lagrangian.
The thing is, since you mentioned this Lagrangian all the time, are we going to see the construction of this Lagrangian section? Or?
I mean, it's not so hard to construct this Lagrangian. You have to first, it's not so hard.
What is your free points of the
I see.
Okay. Other questions? Well, now I have told you that I can deal with that example. So how about a slightly more complicated example? So I can get another affine kind of more Calabi-Yau interior by doing, instead of doing one blow up on each divisor, I can do 2 blow ups on one, 3 on one, 3 on the other, and 5 on the rest, on the third one. And if you do this in a generic way, that's also an affine variety. Check this. And so now you can also construct a diagram, this kind of eigenray diagram for this more complicated affine variety as well. You just follow the same procedure, but now it's a little bit harder to fit the triangles, but you can do it. Okay, so you need to remove, there is some really a constraint there, and you see it corresponds to the fact that 1/2 plus 1/3 plus 1/5 is bigger than 1. Okay. So now you can say, how about now? So you can go, again, you can compute SH0, it's going to be singular. And this time the resolution of the singularity will have an E8 configuration of curves, -2 curves. And you can see the E8 configuration of Lagrangian spheres in the diagram. Those will be mirrored. So this time, how am I going to get it by gluing? So you can first try, you have these, again, these 3 Liouville subdomains, and you can try to glue again, do the same construction, but this time it fails. Because this time, each of these pieces are also not smooth. Okay, so these pieces themselves have these Lagrangian spheres. If you just do the SH0, that's going to give you an AN singularity. So you have to go finer. You have to take a finer cover, and you have to allow non-Liouville subdomains. At least in this construction, you have to. It's okay, it works, but at the end, you have to leave the realm of algebraic geometry. You have to leave the realm of Zariski opens, and you can only construct, well, at least again, in this construction, you can construct something that's rigid analytic. You can glue Berkovich spectrum of some algebras that you can associate to non-Liouville subdomains. This time, they're not finitely generated, they're topologically finitely generated. You don't have to, you can keep working over the trivially valued commutative ring, but you have to take Berkovich spectrum. And you can glue, and I'm saying that this gives you a Berkovich space, which has a map to the analytification of the spectrum of SH0 and is smooth. Yes?
I can ask you.
Okay, so now you can play the same game, but if you want kind of algebraic coherent sheaves, then you have to do some more work and prove that your functor that you constructed maps kind of conical at infinity Lagrangians or conical Lagrangians to algebraic sheaves.
So in this case, you can get an algebraic.
Yes, you can, but the construction that I'm presenting doesn't construct it in that way. I don't know how to construct it using kind of just a Zariski color. Huh?
We can talk after.
Okay. Yes. So this is, do I still have time?
Yeah, almost 15 minutes.
15 minutes, okay.
13.
I must have spoken fast. Okay, so now that's all I wanted to say about this local mirror symmetry and local to global construction. Yes.
So it seems that you can, by playing with these numbers, you can probably get all 80 resolutions in the mirror.
Yeah, that's standard. You can, but it's not the. This is not the Milner fiber.
No, it's a resolution of singularity.
It's not. It's like the smoothing is not this smooth guy is not a smoothing. There's some extra piece. It just has that singularity, but there's more. It's not the cone over that singularity.
It's not just it's the 80 resolution.
Yeah, there is a bit more. Okay, so now let me also say something about how this construction works in the large volume limit case. Okay, so that large volume limit, I just do this two-dimensional example. So I take a 2 torus, and from this 2 torus, I'll remove 3 points as my ample divisor. Okay. So now I claim that there is a way to choose the primitive in the complement of these 3 points, so that the skeleton of the corresponding Liouville manifold looks like in this picture. Okay. So this picture is these kind of orange circles are going to correspond to these kind of these 3 circles. Yeah, this one is kind of a flattened out picture for 2 of these next to each other. Okay, so I'm going to consider a Lagrangian section here as well. So this circle, and that circle is part of the skeleton. It's here. Okay. So I have some. So this the skeleton will contain. So I'm drawing kind of the picture of the Liouville vector field near the skeleton. Okay. So everywhere else, the flow is just kind of taking points towards this point at infinity. On the skeleton, here I have like a minimum. Everything is kind of exiting from here. And here I have a saddle. Okay. And the saddle, you know, this bits are coming in, then these are going out and going to the infinity. The point that I mean. So now I can do the same construction, but this time I can't do it with SH0. This time I actually have to just use this Lagrangian section, because SH0 also has some things that go into here. You have to be careful about that. And here I just use the section and wrapped Floer cohomology of that section for each of. So these are Liouville subdomains. I forgot to say these become just Liouville subdomains. The Liouville vector field is pointing out. Well, I mean, okay, there are limits of Liouville subdomains, which is good enough. They can be approximated by Liouville subdomains. That's good enough. Okay, so then I have kind of this cover by kind of, you can also just take thickenings. That's okay. So let's just take thickenings. Thicken each of these 3 cylinders, slightly thicken them. They become actually Liouville subdomains, and the intersections also become actually Liouville subdomains. We can do the construction with that. It doesn't matter. So then, for the cylinders that contain a puncture, then this Lagrangian Floer cohomology, again, it lives in degree 0, and it has a generator coming from here, x, another generator coming from here, y, and x times y is equal to 0. So this is the local model of like x times y equals 0. It gives me, the algebra gives me two transversely intersecting lines.
I think I don't understand the picture.
Yeah.
So you seem to have like three special points. There's like two where the Liouville flow goes in and one comes out, or what is?
No, you're supposed to imagine that there's a third one and closes up. I just flattened it and drew only part of the.
They start on the top. So you haven't for it.
Yeah, I also didn't draw like the three.
Oh, you didn't. I see.
Yeah, I just I thought one was sufficient to.
It's actually
Okay.
different things.
Huh?
I also thought it was different thing happening.
No, it's the same thing that's happening. It's just I didn't want to.
But then that looks like you have four ends. The next line. What is?
I have three punctures.
Yeah. Where are the three punctures in the next line?
So in the next line, there is not. I didn't draw the full picture. It's just the two of them next to each other. That's enough. It's just repeating.
Okay, got it.
Okay, there was like a Z model,
The middle one.
a cyclic symmetry. Okay. Okay, so then I do the gluing construction, and for each kind of Ki, each big piece, each of these kind of slightly thickened guys, I get this x times y equals 0. So that's this. And then if I'm here, if I look at the intersection, I get x times y equals 1. So that's the C star inside this P1. Okay, so this construction that I explained to you gives this picture. Three P1s kind of identified along points cyclically. Okay, and you also get HMS functor. But the HMS functor, yeah, so let me just leave it at this, but let me ask you this question. So what would happen if I didn't divide it into three cylinders, but divide it into two cylinders, and one of them contains one puncture and the other two contains two punctures? The construction goes through, it will give you two P1s glued attached. It's just not the full mirror. The full mirror is like a resolution of that. And it's missing, the construction is missing this exact Lagrangian circle in between these two punctures. That's not captured in the mirror. Okay, I think this is all I want to say.